On Wednesday, we sort of introduced what carboxylic acid derivatives are, relative reactivity and stability, and we introduced the concept of a nucleophilic acyl substitution. Today is all about nucleophilic acyl substitution. So we're going to get really deep into some specific examples here. And one of those things is going to involve esters. And so reminding ourselves that we previously learned the Fischer esterification, which is controlled by Le Chatelier's principle, which is just the equilibrium thing. Recalling that we know we can make acid chlorides from carboxylic acids. And then Lewis structures, because mechanisms, we're going to draw lots of Lewis structures and making sure we have the right number of lone pairs and we have the right charges. But as I said, all of our learning objectives today are nucleophilic acyl substitution. It's just what is the starting material. So we're going to start with acid chlorides, and then we're going to go to anhydrides, and then we're going to go to esters. Okay, so let's start with the first one. So the 4 P's of nucleophilic acyl substitution . From acid chlorides under basic conditions. Which is 20.4. So acid chlorides are kind of nice because nucleophilic acyl substitution is always under basic conditions for that starting material. That is not always going to be the case, but for this one, it will be. So remember that our acid chloride, we have that acyl group, we have our Cl, this is our X group, right? So that's going to be our leaving group. We're going to react with some nucleophile under basic conditions. So sometimes the nucleophile will already be sort of in that basic form, or we have to add another base. And remember that a nucleophilic acyl substitution means we substitute the X group for the nucleophile. And in this case, I drew H nucleophile, so that would make HX. But you don't actually get HX, right? This is the whole point of having it under basic conditions, is that base is going to neutralize. I guess, sorry, in this case, it would be HCl, right? Because we're talking about acid chloride specifically. So you're not actually making HCl because we have basic conditions. The base is going to neutralize the HCl, right? Strong acid, put in base, it's going to neutralize. Okay, so that's our generic form, remember, okay? So acid chlorides. So let's talk about some specifics. So we know that acid chlorides are at the top of our chart, right? The most reactive. And so we can go down that chart. And so let's look at an example where we start with an acid chloride and we can make an anhydride by starting with a carboxylic acid. So our nucleophile is a carboxylic acid in this case. And last time on Wednesday, I showed you starting with the carboxylate, right? So starting with kind of the basic form of that nucleophile, but you don't have to. You can start with the acid form and then throw in another base like pyridine, for example. Right, so this is a base, remember? And so whether the base deprotonates the nucleophile before or after it attacks depends on the pKa. So in this case, remember that carboxylic acids are quite acidic, right? That's why acid is in the name. And so this proton is pretty acidic. Maybe I'll draw out the bond here. So that proton right there is pretty acidic. And so in the presence of base, it's going to get deprotonated right away. Okay, so this is a proton transfer, right? So proton transfer. And all that's doing is making the sort of more nucleophilic or the basic form of that nucleophile. And then our counter ion is now this protonated pyridine or pyridinium. Okay, so now we've made our nucleophile, right, a little bit stronger. So now it's negatively charged. Now we can do our addition step, right? Remember, nucleophilic acyl substitution has that addition elimination mechanism. So now we're going to do our addition step where our nucleophile attacks our electrophile, break the weakest bond. Remember, our electrophile is always that carbonyl carbon on our carboxylic acid derivative. Here's addition, because we've added the nucleophile to form our tetrahedral intermediate. We have our chlorine still attached, and we have our nucleophile attached. We still have our pyridinium counterion. Okay, so we've made our tetrahedral intermediate through addition. Now we need to do our elimination step. Remember, in elimination, we lose our leaving group. So our lone pair pushes down to reform the carbonyl. Leaving group leaves. And that will form our anhydride. And then our byproduct is our pyridinium chloride. So again, it's HCl that's been neutralized by the base. Okay, so hopefully you can map on that generic mechanism that we talked about on Wednesday, right? Addition, elimination. That's the core of this mechanism. All we did was a proton transfer first to make a little bit of a stronger nucleophile based off of the pKa's of our nucleophile versus our base. Okay, so that's acid chloride to anhydride. Sometimes you do not deprotonate first. Sometimes you deprotonate later. So let's talk about acid chlorides to amides. So again, I'll use a very specific example just to show you, but it doesn't matter what the R group is. So there's our acid chloride. So we could have an amine as our nucleophile. So amines are already basic, right? They're already quite nucleophilic. And it's very, very difficult to deprotonate an amine, right? N minus, not very stable. So we're not going to do that right away. But we could add in more base if we wanted to. You don't have to. You can actually just use more equivalents of your amine, but we'll just say as an example, we could do this. So in this case, this base is not strong enough to deprotonate this proton yet. So it's not going to do that. We're going to start with our addition step. So we do our addition step, nucleophile attacks electrophile, break the weakest bond. We will form our tetrahedral intermediate. Now we have a positively charged nitrogen here. Now this proton is much more acidic, and our base can come in and deprotonate that. The base can pull off that proton. So now we do our proton transfer. To make that nitrogen not be positively charged anymore. Okay, so we lost water in that process. Sodium is our counter ion. Okay. So we made our nucleophile neutral. Now we're ready to do our elimination step. Push down to reform the double bond. Leaving group leaves. Nothing is different. This is elimination. And now we have formed an amide, right? So using an amine nucleophile gives us an amide. And then our byproduct in this case is sodium chloride. that kind of make sense, right? All of these are under basic conditions, but where that proton transfer happens can depend on the pKa's, okay? So if you have a very acidic proton, it'll happen at the beginning. If you don't, the nucleophile will attack first and then you do it. But the mechanism is the same, right? Addition, elimination. Those are the key steps. We just have this additional proton transfer, okay? Okay, so we did anhydrides, we did amides. We could also do esters, right? So we could do some acid chloride plus an alcohol or an alkoxide. So I'll just draw an alcohol in this case. Again, if you are not starting with the alkoxide, you do need to add in an extra base. So again, I'll use pyridine as an example. And remember, the overall reaction is going to be replacing the X group with your nucleophile. So our overall reaction should be replacing the chlorine with our nucleophile, which is OMe. And then our byproduct will be our pyridine quenched HCl. That's a blue proton. So my first challenge for you today is to draw this mechanism. It's the same, right? It's the same. So this is a way to double check if you're understanding how this mechanism works. I will post the answer with the notes. But I've shown you two with acid chlorides. I want you to do the third on your own, and then you can double check your answers. But again, try to do it with your notes closed first to try and see if you're understanding how these mechanisms work, okay? So that is to form esters. Okay, so that's all of our acid chlorides, yes?
So when you say that pKa transfer happens, is it like lower pKa happens later, higher pKa?
Yeah, so the pKa of this proton is very low, right? And so that makes it go faster, right? So we're gonna do it earlier. So we did this in the first step. Whereas here, this pKa is very high, and so it's gonna go later. Yeah. So the more acidic the proton, the easier it is to go, right? So it's more likely to go later, or earlier, excuse me. Good question. Okay, so that's all of our acid chlorides to various carboxylic acid derivatives. You can technically do acid chlorides back to the carboxylic acid itself, right? So I could take an acid chloride, add water as my nucleophile, and make a carboxylic acid. Right? So this follows the exact same mechanism. We can do this, so you can do this, but why is the question? Because remember, normally we are making our acid chloride from the carboxylic acid. So remember, this is our thionyl chloride. So this is a recall reaction back from 13.7. Okay, so yes, you can do this. You just normally don't because you're normally going in the opposite direction. Okay, but it is possible. It is possible. Okay, is that kind of making sense? Just sort of that general form, replace X, put in nucleophile, right? Addition, elimination. Let's do a chiming question to see if we can go backwards now, because going forward is one thing, going backwards is a little bit harder. Okay, so here I would like you to propose the starting material for the following reaction. There can be more than one. So I've given you both a carboxylic acid derivative and a potential nucleophile. I've given you the product. I've also given you the byproduct. So pay attention to that. You will not always be given the byproduct, but I'm giving it to you this time. Does that change the answer? Feel free to chat with your neighbors. See if they're getting the same answers as you. 10 more seconds, get your answers in. All right, let's see what we got. Nice. Okay, great. So most people are getting that A is the correct answer. D is the tricky one because if I had not given you the byproduct, D would have been fine. But I gave you the byproduct, so it has to be A. So let's go through how I think about this. So I totally get why you would think that, because D normally would work to make the major product. Okay, so in this type of situation, right, you're supposed to give us the starting materials. You were given pyridine, and you were given this plus this. Okay, so the way that I would approach this problem, right? First thing, I recognize that this is an ester, right? This is an ester, which means that it's a carboxylic acid derivative. So then I would break down this carboxylic acid derivative into the acyl part and the nucleophile part. So this is the bond that was being made in this case, right? So if that's the bond being made from nucleophilic acyl substitution, my nucleophile has to be this part. So you can either make the alcohol, or if you would have drawn an alkoxide, that would have also been fine, because those are both nucleophilic versions of the same thing. So the alcohol, and then on the acyl side, we know that we would have replaced some X group here, right? And so that's why normally an acid chloride or an anhydride would be fine, except I gave you the byproduct, which shows you that the X group was a chlorine. So then this has to be a chlorine. So that's how I would break down this problem. Questions on that? I know it's harder to go backwards. It's harder to go backwards. Okay, so that's acid chlorides. That one's pretty straightforward. Now let's go to anhydrides, where things get a little bit more complicated, because now we have sometimes basic conditions and sometimes acidic conditions. So same type of learning objective, 4 Ps of nucleophilic acyl substitution from anhydrides and nucleophiles under basic and acidic conditions, which is 20.5. Okay, so let's remind ourselves, anhydrides look like this, right? This is our X group. Don't be confused because it looks weird. It's just an X group. It's not different. We have our nucleophile, either basic or acidic conditions. So I'm going to leave that blank for now. We're going to replace our X group with our nucleophile. And then H goes with our X group here. So it makes a carboxylic acid as the byproduct. Okay, so anhydrides. We can't go to acid chlorides, right? Because that would be going up the chart. So we can go to esters or amides. So we're going to start with amides because it's a little bit more straightforward. So anhydrides to amides. And it's a little bit more straightforward because it's always under basic conditions. Remember, amines are bases, so they kind of have to be under basic conditions. So let's start with an anhydride, like so. We're going to use an amine. Let's do a primary amine this time. Doesn't actually matter. So here's our amine. Okay, so in this time, I'm just going to assume I have extra amine that's going to act as my base, because this is already This is already a base. So again, it's really hard to deprotonate an amine to get N minus. That's not favorable. So we're not going to do that first, which means that we're ready to just do our addition step. So we have our nucleophile, which is the amine, the nucleophile. Our electrophile is always that red carbonyl carbon, right? A nucleophile attacks electrophile, break the weakest bond. This is our addition step. So we are going to form our tetrahedral intermediate. Okay, so now my nucleophile is positively charged. We don't want that. So I have more than one molecule of our amine in the flask. So it's going to act as a base to deprotonate one of those protons, quench the positive charge. So this is a proton transfer, similar to what we showed before, right? We just need that nucleophile to not be positively charged anymore. We still have our X group attached. Again, don't get confused that it's a weird looking X group. It's just an X group. And now our counter ion is this ammonium. So positively charged nitrogen. Okay. So we did our addition, we did our proton transfer.
Unsymmetrical anhydride. Is there part of the R group that tells you which one gets the nucleophile and which one gets the alcohol?
Yeah. Okay, so that's a good question. So if your anhydride is not symmetrical, so most of the time you're working with symmetrical anhydrides because it is difficult to differentiate. Technically, if one of them was way more like electron deficient, it would be more electrophilic and therefore it would go there. But like almost always you're going to be dealing with symmetrical anhydrides for that reason. Yep. It's a good question. All right. So now we have our neutral nucleophile, which is good. We're now ready to do our elimination step. So that entails push down the lone pair, right? Collapse the tetrahedral intermediate to reform the carbonyl. X group leaves. So now we've replaced our X group with our nucleophile, and we have generated a carboxylate, and our counter ion is still this ammonium. And we have formed our amide, right? So again, starting with an amine nucleophile gets you an amide at the end. Okay, so anhydrides to amides, always basic conditions. So where things get a little bit more complicated is when we talk about anhydrides to esters. So if you recall, we've talked about this previously, alcohols are worse nucleophiles compared to amines, right? So they're not as good of nucleophiles. Therefore, we have two options. So two mechanisms. We can either make a stronger nucleophile, which is our basic conditions, or we're going to make a stronger electrophile, which is our acidic conditions. Okay? So all of that is driven by the fact that alcohols are not super great nucleophiles by themselves. So we have to bias the mechanism, either stronger nucleophile or stronger electrophile. So our stronger nucleophile would be to use an alkoxide as your nucleophile, right? So an actually negatively charged oxygen instead of a neutral oxygen. So our overall reaction here, again, you have your anhydride. There's our X group. we're going to use a stronger nucleophile, so a negatively charged oxygen. And that's going to give us our ester by replacing our X group with our nucleophile. And then our byproduct is going to be our sodium carboxylate. So my second challenge for you for the day is to draw this mechanism. Again, it's not different. This is basic conditions, so it's very similar to all the ones that we've been doing, right? Basic conditions. I want to walk through the acidic conditions though, because that one's a little bit different. Okay, so that's again my challenge to you. I will post the answer to this at the end of the notes, so check that out if you would like to check your answers. But the other option, making a stronger electrophile, which again means that we're going to use an acid catalyst, has a couple more proton transfers. It's still not a different mechanism. It just looks a little bit scarier because there's more proton transfers. So let's do the same reaction. We're going to start with our anhydride, but we're going to use a neutral alcohol. So we first need to add our acid catalyst to make a stronger electrophile. So we're going to use H2SO4 again, because that's our kind of classic acid. Doesn't have to be. Right? So we're going to make our electrophile, which again is this carbonyl, more electrophilic. Remember how we talked about how the carbonyl oxygen is the most basic site on that molecule, so that's where it's going to protonate. Okay, so this is a proton transfer to make a strong electrophile. HSO4 minus is our counter ion. Okay, so all we did there was protonate to make a stronger electrophile. We've activated our electrophile. We are now ready to do our addition step. So I'm going to have a neutral alcohol, so say isopropanol, for example. The nucleophilic part, the lone pairs on the oxygen of the alcohol, which now can nucleophile attack electrophile, break the weakest bond. This is our addition step. Okay. Counter ion is HSO4 minus. Okay. So again, we protonated to make a stronger electrophile, and then we did our addition step. Nucleophile attacks electrophile, break the weakest bond. Now, our carbonyl oxygen is neutral, right? Because it has that extra proton on it, which is fine. But our nucleophile is positively charged. Again, we don't want our nucleophile to be positively charged at the end of this reaction. So we need to deprotonate it. We also generally don't want to make negative charges in very strongly acidic media, right? And so we often in strongly acidic media will protonate our leaving group before it leaves. So in this case, this is our leaving group. We want to make it a better leaving group by protonating it. So I'm going to have our leaving group oxygen here. Grab that proton. Probably could have drawn that in different orientation to make my life easier, but didn't. So this is also a proton transfer. Technically, it's 2 proton transfers. You can draw it in 2 steps if you want. Like so. Okay. So again, let's track what we did here. Our nucleophile oxygen was positively charged. Now it's neutral. So we took a proton away from that to make it not positively charged anymore. Then our leaving group, right? We made it a better leaving group by protonating that oxygen. So technically we did 2 proton transfers kind of in one. But it's just proton transfers. All we did was move a proton over 1 oxygen. Now we are ready to do our elimination step because our leaving group is ready to leave. So again, our red oxygen over here is going to push down a lone pair to collapse the tetrahedral intermediate, regenerate the carbonyl, leaving group leaves. So we have our HX there, and we have our ester, but it still has this extra proton on it. This way. Right? So we did our collapse. We still have this extra proton, right? Because we didn't want to have a negative charge over here, so we still have a proton on it. So our last step of the mechanism is just to deprotonate using our counter ion or solvent or another substrate. Proton transfers happen a lot with a lot of different things. So it's our last proton transfer, which finally gets us to our stable neutral molecule. And we regenerated our catalyst. So that shows us why we can just throw in a little bit of acid and it can do this multiple cycles because you regenerate it at the end. Okay, so that's a lot of steps, right? It looks like a lot of steps, right? But really, it's the addition step and the elimination step are the key steps. Everything else is just proton transfers to make the charges work out, right? That's basically how all these mechanisms work. But I get that there are kind of a lot of moving pieces, right? So you have to be thinking about like, okay, you know, am I going to deprotonate this in strongly acidic media? No, you're not going to make a negative charge. So we have to attack first. Now it's positively charged. We don't want that. So now we have to do the proton transfer, right? So just like trying to break it down and think about it step by step by step. In these types of mechanisms, it's really common for people to either drop carbons, right? So dropping number of bonds or dropping formal charges. So this is where going back and double checking, like, okay, how many bonds does my oxygen have, right? Here, my oxygen has 3 bonds. It better be positively charged, right? Those are really, really common mistakes. And so trying to get comfortable with looking at a structure being like 2 bonds to oxygen, that's neutral. 3 bonds to oxygen, that's positively charged, right? 1 bond to oxygen, that's negatively charged. Ooh, that's really bad, right? We don't want negative charges in this strongly acidic media. So like those are kind of the little checks that you can be doing as you're going through the mechanism to try and like catch those little mistakes, right? Questions? I know that it's a lot of steps. I know that it's a lot of steps, but I promise you, it's not actually as bad as it seems, right? Addition, elimination, those are the 2 main steps. Everything else is proton transfers. Okay? Okay. So as just practice, let's think about what happens if your anhydride is cyclic, because sometimes you will see this. So here, this is an anhydride, succinic anhydride. It's not different just because it's in a ring. Let's number our carbons just for that sake. Again, I'm going to kind of arbitrarily decide that this one is my red carbonyl, which makes this oxygen and this carbonyl my X group. So if I were to mix this with sodium methoxide, what do we think we're going to get? So I'd like you to try and draw that. It's not actually different. It just looks a little different. But the reaction is the same. We want to make sure we're not dropping any carbons. So remember, when doing a nucleophilic acyl substitution, we're breaking this bond between the red carbonyl and the X group, right? So this is the bond. Oops, that's going to break right there. So how would I approach this problem? I would try to draw it in almost the same orientation. Numbering my carbons, 1, 2, 3, 4. Okay. So my purple part is down here. Right, so I broke the bond between the purple oxygen and the red carbonyl here. And I need to replace the X group with the nucleophile. And then my carboxylate should be negatively charged, and my sodium is my counterion. That make sense? Look at the functional group, right? It didn't actually change. It's just a little bit different because our byproduct is attached to kind of our main ester product, but it's not actually different. Okay, I know that it looks weird. I know that it looks weird, but just trying to take it step by step. Focus on the functional group that's happening. What bond is breaking, right? Break that bond. Place the X group with the nucleophile. Okay. All right. So that was acid chlorides and anhydrides. Let's recall some stuff about esters. So we have now learned that you can make esters from acid chlorides or anhydrides plus an alcohol, right? We just went through a couple of examples of that. Recall that you've also learned to make esters, excuse me, from Fischer esterification. So we talked about this both in 16.8 and in 19.14. And so that is from a carboxylic acid and an alcohol. Under acidic conditions, it's a reversible process. So that's why I have the equilibrium arrows. We've replaced our OH with our OR, and water is our byproduct, right? So this reaction you have learned. We talked about how if you want to push this towards the ester, you use a Dean Stark, which removes water. But this is a reversible process. If you think about this in reverse, that's an ester going to a carboxylic acid, right? Goes to a carboxylic acid. That is the reverse. So this is a reaction that you already know. This is our next learning objective. So the 4 P's, again, it's a nucleophilic acyl substitution. From esters to carboxylic acids, which we can call hydrolysis, right? So we're hydrolyzing our ester under acidic and basic conditions. So the opposite of the Fischer esterification is the acidic conditions. We will also talk about the basic conditions, but not till Monday. So let's start with our acidic conditions, because that is the opposite of the Fischer esterification, which you have already learned, which is section 20.8. So now let's draw our reaction in the opposite direction because we're going in the reverse. So there's our ester. Now water is our nucleophile. Acidic conditions, so we better have some acid around. We will make our carboxylic acid and an alcohol byproduct. So again, we're under acidic conditions. So when we're under these strongly acidic conditions, we want our organic molecules should have positive charges, not negative charges. So again, similar to the anhydride case, we are just going to do the proton transfers such that we never have negative charges. Okay, so let's start with our ester. So again, we're in strongly acidic conditions. We can't just attack the carbonyl. We can't just do our addition, or we'd make a negative charge on our carbonyl oxygen. Oops. Okay, so first we got to protonate, just like we did in the anhydride case. We're making a stronger electrophile. So this is our first proton transfer step. Okay, all we did, proton transfer, made a stronger electrophile. Now, these are all reversible reactions or reversible steps. Water is our nucleophile. Right? So now we have a stronger electrophile. We can do our addition step. Nucleophile attacks electrophile, break the weakest bond. Okay, so I just added in HSO4 minus, there we go. Okay, so all I did was I added in my nucleophile. I did my addition step. Now we have our positively charged incoming nucleophile. We don't want it to be positively charged anymore, so we need to get rid of that. So we need to do a proton transfer. So this time I'm going to draw the proton transfers in two separate steps just to show how that goes. So my counter ion is going to grab one of these protons. I'm going to go all the way down to the next page. Okay, and I regenerated my acid catalyst, like so. So this was just a proton transfer to get rid of the positive charge. Now I'm still not ready to do my elimination step because if my leaving group were to leave, it would form a negative charge, right? You can't form negative charges in this very, very strongly acidic medium. So we're going to make our leaving group a better leaving group by protonating it. So we're doing another proton transfer. To make our leaving group positively charged, so now it's ready to leave. Okay, we've made a stronger leaving group, so it's easier to leave. Now we're ready to do our elimination step. red oxygen pushes down, leaving group leaves. And we've generated our byproduct, which is this alcohol. So now all we need to do to get to our final product, right? We just need to deprotonate here to make a neutral stable molecule. So again, we can have our byproduct come in, just pull off that proton. And we regenerate our H2SO4. So again, it shows that it's a catalyst. So it's the same addition elimination mechanism. All that's different is we did a bunch of proton transfers to make sure we only ever had positive charges. Okay. All right, that's all I have for you today. We will continue with esters on Monday and go through the basic conditions in addition to the acidic conditions. Remember to do those challenge mechanisms. I will post the answers to those with